to everyone. Because located in the northeastern part of India, sometimes it is this information is missed out by many. Like this is a center which deals with remote sensing applications, satellite communication, space science activities, and under that, like we have under space science, we have the Doppler weather radar set up in Cherrapunji, and satellite communication is helping in EduSat programs and programs supporting the for medical facilities. And under remote sensing, we have several scientists working here in the field of agriculture, forestry, soil sciences, geology, and so on. So and I'm working in forestry, and in fact, I have been working in the field of optical remote sensing, and recently taken up the task of microwave applications in forestry. So whatever I have understood and the through the practical studies, I would be sharing with you in this session. So to start with, as everybody, all of us are aware, the remote sensing, when we say the imaging remote sensing, it actually deals with optical, and then we have the radar remote sensing, and we have lidar remote sensing also. And each of these domain has its own advantages and disadvantages. Like most of the studies are being done using optical remote sensing, and in this field we get the data, many of the data freely available, and often the data analysis and data processing is little comparatively simpler than in the radar and the lidar. Then when we focus on the radar remote sensing, it gives little enhanced information about the forest. And further, when we go to the lidar remote sensing, it gives much more precise, and like at individual tree level also we get information. So let us now focus on the synthetic aperture radar SAR applications in forestry. So as I have just mentioned here, we have the optical and the non-optical. And as we move from the optical range in the electromagnetic spectrum, the wavelength is increasing, and thereby helping us to generate information in this longer wavelength. And the type of information varies from in between these two domains. So like we have the visible domain, and the infrared, we have further in that we use remote sensing uses the red region, blue region, and green region. And then comes the infrared. And infrared is the domain, like domain in the electromagnetic region, where most of the forestry studies are carried out, because it is the field which gives most of the information of the tree canopy, the forest cover, because for the interaction with the canopies, and how it is happening, we'll come to that. Further, we have the microwave region, where we have several bands, and our study mostly it starts from C band onwards. X band is also used in the remote sensing studies, but mostly we are doing our study from C band onwards. And in this SAR applications, in the current scenario, C band and L band is mostly being used. So synthetic aperture radar, as we all know, it is an active sensor that transmits the microwave radiation, and then it receives back the signal, and that return signal we name it. It is named as the backscattered energy. And here, the advantage of using microwave remote sensing, I'm sure everybody by now is aware, but in the forestry context also, here the sun angle variation in the optical data, what we get to see in the optical data is least in this microwave region. And further, atmospheric variation and cloud do not affect the microwave region like it happens in the optical domain. So as I have just mentioned here, the spectral characteristics vary between the optical region and the microwave region. Here, this graph actually is a popular graph which is always presented to understand the spectral characteristics of the vegetation, how the vegetation is behaving in the optical region. So what is happening here? Here we see little reflectance in the green region, and further, and when we move towards the infrared region, we see a peak in this in the curve, and this peak is due to the infrared region reflectance. And this is what is used mostly in the forestry studies to understand the various forest characteristics, forest cover, forest stress, forest species discrimination, and so on. And likewise, we have the sphere region where the spectral reflectance actually comes down due to the water content in the vegetation. So based on this reflectance characteristics, the optical images are analyzed for various applications. Further, when we come to microwave region, it is an active system, as I said. Optical systems are dependent on the solar illumination, but microwave systems are independent of the solar illumination, the cloudy conditions, the dusty conditions, and it has advantages we can get images during the cloud cover conditions, particularly during the flooding and highly like for our region, northeastern region is most of the time covered by clouds. So for it is very advantageous to use microwave data in our region, in the northeastern region. Further, we estimate biomass using optical also, but when we move towards the SAR region, we get the mapping of the precise mapping of the higher biomass densities also. Then we further like we have several other characteristics, we will come to that, like surface roughness, the directive properties, and polarization and frequency. All these characteristics actually add to the identification and interpretation of the images, SAR images, for forestry application. Is it fine? The slides are visible? Hello?
Yes, ma'am, they are visible.
Yeah, okay. So moving on to next, as I said that optical, this is the optical RGB image. You can see that when we use this optical image, we can see some it is a mosaic of several images for the state of Assam. So when we mosaic such images, due to the atmospheric conditions, sun angle, and so on, the optical images are affected. The mosaic is affected by such variations. Of course, there are methods to correct it, but still, such variation, optical images suffer from such effects. So further, when we see the SAR image, we get a mosaic in the RGB image also. And what is happening here, the red portion actually in optical image, it is due to the infrared reflectance, and this image is called the false color composite. False color composite in the optical region, and here all the forest occurs in the tonal variation of red region. So further in RGB, here we have made the composite using NIR band, red band, and green band. In RGB image, we make the mosaic using the various polarizations like HH, HV, or VH, and so on. So this is one example from Assam, where the images are the RGB images made, and then SAR images can give us images in various polarizations and different incident angles. And these things actually I have already told you that it is the backscatter energy and how the Earth surface is behaving. Actually, in radar images, the thing what we need to understand in the interpretation is that it is affected by various characteristics like surface characteristics, geometry, moisture content of the object, and so on. And further, so that's how microwave becomes very, very important in the forestry study due to the complex structure of the forest. When we see the forest, we have the higher canopy. Then we have further down, we have further lower canopies, and these stratifications actually in the optical domain we get less information compared to the microwave. So using microwave, due to the various polarizations and the incident angles and so on, we generate various applications and more information compared to the this thing optical. And radar images are better for canopy structural parameters determination. So now the radar transmitter penetrates into the characteristics which radar is advantageous over the optical is that it can penetrate into the canopy, forest canopy, and it interacts with the various leaves, branches, stems, and underlying soil. So what is happening here in optical image when we see in the infrared region, as I have just discussed, in the infrared region, actually it interacts with the leaves. It interacts with the leaf internal structure and various pigments that are present in the leaf. But in microwave, what is happening? It is interacting with the structural component, the various leaves, twigs, branches available in the forest. And the image interpretation depends on the magnitude of the transmitted energy, depending on the forest properties. Forest properties like what is the type of the forest, what is the species composition, and what is the water content in the forest, and so on. So radar images are interpreted at different frequency or wavelengths and depending on the penetration capabilities of the radar wavelengths. So it depends on, as I said, it depends on various components. And another important factor is the volume, the timber volume of the forest, which actually gives the biomass content in the forest. So thereby, the timber volume, the vegetation height, and these are the characteristics that we get most like important information we get using microwave images. So now we have different bands, as I said, and different band interacts. X band interacts with the leaves, twigs, and higher canopy structures. Further, C band, further it goes little down like leaves and small branches. L band, it will go up to the major branches and trunks. And P band, further, it is the longer wavelength and it reaches the further down and it gives the interaction with the tree trunks and even the ground surface also. And thereby, actually in a forest, various properties, the scattering properties are defined, which are the various like diffuse scattering from the ground, direct scattering happens from vegetation components, double bounce we will see, and then we have corner reflection also happening within the forest, which is generally told that it is happening in the buildings and in the urban areas, but in forest such double bounce and corner reflections are occurring. Then we have volume scattering, diffuse scattering, and so on. There are various scattering components that are identified within a forest. So a combination of all actually leads to the interpretation of the forest areas. So when we come to these components, and these components interact depending on the radar parameters like frequency or wavelength, polarization, incidence angle. Then we have the surface parameter. with which it is interacting, the dielectric constant, surface roughness, and structure and orientation of the surface. Particularly for us, it is the forested area, vegetation area. And as I have said, the penetration capability of each of the band and its interaction within a forest with the trees can be imagined from this particular diagram. So how wavelength it is affecting? As I have said, the pictures are explaining what is happening within the forest, that each of the structural component is leading to the backscatter the characteristics within the forest. And we know that the longer wavelength, the deeper is the penetration within the forest. So X band is dominated by leaf interaction, mainly from the top of the canopies, C band by the twigs and the small branches, and L band penetrates further deeper into the trunks and to some extent, depending on the forest density, to the ground surface also. So we have various satellites that are working in C band, X band, and which are providing us information on this forest aspects. Further, when we come is the polarization characteristics. The polarization is the key characteristics of the radar signal propagating into the tree or vegetation that determine how the signal interact with the trunk and the crown components. So we have I am sure you must have gone through the polarizations that are available. We have various horizontal, vertical, and cross polarizations also. The HH and VV are called the co-polarized or the light polarized, and HH and VH are called the cross polarized. And each of this has a different role to play within the forest. So when we say within a forest area, we have different components. Like some are tropical trees with wider branches, big leaf structure, and further when we go to the temperate region, we have the tall conical shaped forest, and the leaf structure also varies. So the radars provide information about all these. And different depending on the orientation and the size of the components, and most important is that backscatter from copolarization VVHH is typically stronger for surface components, whereas the energy backscatter from copolarized detection is from the volume component. So moving next is the scattering. So as I'm saying, the scattering component, the various types of scattering is occurring within the forest. So when we see generally within a land use category, we have various scattering components like diffuse scattering, where the light is depending on the surface roughness, the light is diffused. And there are specular, where light is reflected back opposite to the incident radiation. And there are corner reflectors like buildings, where the light is reflected to the ground, buildings again to the ground, and thereby which gives a very bright signature tone in the radar images. So within the forest, we get same scattering components also occur, but the most important within the forest is the volume scattering, where multiple scattering is occurring within a tree, within the branches, within the leaf components, like that, and where due to the multiple scattering, the backscatter also improves. So likewise, as I said, X band and C band will interact with the tree canopies. L band will go a little further deeper, and the volume scattering occurs within the forest. So likewise, we have volume scattering, volume and surface scattering from the forest surface. Why surface scattering is important? We will come to that. Like in a flooded condition, also, how much area, vegetated area, is inundated. So, in such cases, the surface scattering within a forest plays an important role. So it depends on the number of trees, size of the scatterers, the wavelength that we are seeing, the dielectric constant, shape and orientation of the leaves, etc. So now we have seen a dielectric constant that we have mentioned here, and we will come to that a little later. So as I said, the scattering depends on the surface roughness. So surface roughness depends again on the wavelength and the incident angle. So then how it is defined? The surface roughness, actually H is defined based on the is a function of the wavelength and the incident angle. So that's why like we say that a surface may be smooth to a certain wavelength and incident angle, but the same surface may be rough to the other incident angle and the other wave. So thereby, depending on the wavelength you are using, the interpretation has to depend accordingly. So here there are two criterions that are often discussed. Is one is the Rayleigh criterion, and another is given by Ulavi on the height variation. So as I said, is particular surface may vary as in X band and L band. It may be rough, and sometimes a surface in L band may be smooth, but it may be intermediate roughness in the X band. So then when we see according to the incident angle, it is seen that as the surface roughness, surface roughness and the incident angle, this particular diagram will explain further, is that here is the rough surface and is the backscatter intensity. Then we have the intermediate and the smooth surface. So what is happening? The backscatter coefficient of smooth surface decreases steeply with increasing incidence angle. This backscatter coefficient of rough target does not decrease so steeply with increasing incidence angle. So the rough surface will give intermediate backscatter in the various incident angles. But the smooth surface will appear darker with the increasing incidence angles. So this is what is explained here. A flat smooth surface generally appear black or dark because all energy is reflected away from the sensor. A calm water body will appear dark in the radar imagery. A forest canopy is an example of the rough surface or diffuse surface will appear gray in color with varying texture. Rougher surface scatter more energy in all directions, including back to the sensor. Therefore, rough surface appear brighter. Surface roughness is described as a function of this we have already discussed. Fine. So now we come to the dielectric property of the object with which radar is interacting. The dielectric constant is actually controlled by the moisture content. And why it is important is that radar backscatter is influenced by the amount of moisture in the vegetation and the soil, thereby affecting the absorption and the propagation of the backscatter. Increasing moisture content actually reduces the penetration of the radar signal through a vegetation canopy. So if the water content is more in the vegetation, and therefore it will block the incident radiations, and thereby this particular characteristics will also help us to determine the type of vegetation and even the phenology that we say that is the greening cycle, or whether it is changing. We say that phenological studies are being done and climatic studies are being done. So in this particular thing, like using this property, you can study the water content of the leaves and how it is varying with the season and over the years also. So increasing moisture content reduces the canopy of soil. So this is what we have discussed. So now some observations that we see is that vertically polarized light is highly attenuated by the vertically oriented components of the trees. These are some few things that we need to remember while interpreting the radar image. The brighter return on light polarized HH or HV in comparison to in comparison to HV, the greater the contribution. So HH and VV contributes is more contribution is from the surface scattering. The brighter return from cross-polarized is the greater is the contribution from the volume scattering. We call it internal canopy scattering. And the moisture content, as we have seen, the greater the dielectric constant, the higher the backscatter return. And that's how the leaf water content is determined by the active radar systems. So when we interpret the image, keeping all these characteristics in mind, the SAR interpretation will depend on the darker areas. The darker areas in the image represent low backscatter, while brighter areas represent high backscatter. So backscatter of a target area at a particular wavelength will depend on the physical characteristics of the target properties, the moisture condition, and the wavelength and polarization, as we have already discussed. So further, there are various literatures available, and recently I have gone through the survey SAR handbook that gives the detail of the SAR interaction within a forest and various applications also. So it says that HH indicates predominance of the double bounce, while VV is related to the surface scattering, and HV, as we know, it is the volume scattering, and that's how it is important in the vegetation study. HV component gives the volume component, and that's how it is important in the biomass based studies, forest biomass estimations. So due to the limited light penetration into the vegetation, X-band rarely used for characterizing vegetation canopies for monitoring underneath vegetation. With moderate to high resolution capability and increased vegetation penetration, C-band data has been seen as a good compromise between X-band and the long wavelength band like L-band. So L-band SAR are mostly useful for mapping activity underneath the vegetation and due to the high penetration capability, and L-band is a good example where we can use the high and longer wavelength for vegetations. So we have also discussed about the incidence angle, and this is how you can see the interaction, how it actually interacts, it determines the forest type. So this we have already discussed, the vertical component and the HH component. And so most important for biomass studies, we use the cross-polarized. So now coming to the applications where SAR data is being used. The SAR data is used for various forest mapping, regrowth mapping, forest structure, biomass, forest height, and vegetation classification. See, out of this, we get good information on vegetation classification and also regrowth and forest mapping. But these components like forest structure, forest biomass, forest height, these are the categories where SAR data is more valuable and provide more information. So just to discuss here, the Forest Survey of India, yearly it brings out the forest cover map of entire India using optical data. But here what we can see is that in this particular forest cover mapping, we can also use the SAR data. Like SAR data can be used in most in the available areas. To observe the water content and the forest cover characteristics also, particularly using the C-band, that will be an additional information in the ongoing exercises that is being done. And now recently, Forest Survey of India is also including the SAR data analysis for the biomass assessment that has come out recently in the State of Forest report, 2017. So now here, as I have said, that the radar backscatter is actually sensitive to the vegetation biomass, the everbrown biomass. Here, for biomass estimation, mostly the L-band data and P-band data are preferred over the smaller wavelengths. So here, we have seen various studies have shown that the X band actually can bring out the biomass in the forest approximately 40 tons. Then C band can go up to mapping up to 80 tons. L band can go for mapping up to 120 tons. P band can map up to 200 tons. So that is the advantage over the optical. Where optical, we will go up to say 80 to 100. So that, and using SAR band, we can go up to for mapping of the higher density and the higher biomass zones. Another example is shown the biomass and the backscatter coefficient. It is seen in C band, L band, and P band. So here what we see that in higher, in different polarizations, of course, but when we go to the higher biomass zones, there is overlap and there is intermixing. The classification is often overlapping with the biomass, increasing biomass. But when we go to the P band, the separation is improved greatly, and we get a higher, better zonation of the forest biomass available in an area. So this, just to share an example with you, is the forest biomass map in the using L-band data allows pulsar for the state of Assam. So here, what has happened here, we have this green colors. What you are seeing is actually the forest density map taken from Forest Survey of India, and this is used for distribution of the sample points within the area. So using the sample plots, we we get information using the inventory points. Inventory, it actually collects the girth information of the tree, the height information, the tree species, etc. In a plot level, and with those information, the ground inventory, using the ground inventory point, the biomass of individual sample plot is assessed, which is then assessed with the SAR polarization L band, and then we generated the biomass map for the state of Assam. This is actually a level 1 biomass map. Here, further improvement will be carried out using this date. This ground inventory point here used is the Forest Survey of India inventory points, but it needs improvement, like with additional sampling in the ground, and also with the type of the forest and the density, because here the biomass will vary with the forest type and forest density. So therefore, the ground inventory also should have information on the different forest type and the density, which will be correlated with the backscatter characteristics of the SAR image, and then the biomass map is derived. So accordingly, using this, we get the distribution, the spatial distribution of the forest biomass within a particular area. And this information is useful for various forest management activities, in the recent days, the climate change studies use lot of data and lot of information using the forest biomass data and how it is changing over time, and which region is contributing to how much biomass, and accordingly the management measures are taken for any particular managers. So next application using SAR comes to deforestation and degradation study. So similarly, using the like as I have told, the cross polarized, the VH and HV are actually the volume scattering components. But further, using the bands like C band, we can measure the surface structures, the how the volume component is removed from the image, and that's how we can see that how much area is degraded. The the how much area is deforested or degraded, because it reduces the volume scattering and from the particular area. It removes the volume scattering is the vegetation component. It is removed, and then we get backscatter from the soil beneath. So that this information can give us an overview of the deforestation and degradation in a particular area by doing the change detection and the time series analysis. So here is a comparison for say shifting cultivation areas or the forest fire, which is also a result of the patches are burnt in a particular area, and such plots are left behind where they carry they continue the cultivation, and after 1 year or so the plots are left idle for vegetation regrowth. So and in northeastern regions, such shifting cultivation or the zoom areas are widespread, and this is one of the leading causes of deforestation in the northeastern region. And because here the shifting cultivation here a specific phenomenon is that for burning the for this cultivation practice, it is practiced in in a defined sloped area, and due to this for this practice, the vegetation in the particular area is cut down or it is directly burnt, and the soil is left for the cultivation. So such areas lead to heavy deforestation in a particular area. So using sentinel data, sentinel multispectral image, we can map such areas. And but what happens here, that often such plots are gets mixed up with the nearby plots, which are the wasteland or open scrub areas. So that's how we try to use. This is just a recent exercise that we are actually continuing now, and here what we have seen, that for this comparison, and you see for this shifting cultivation, what we are doing, these actually leads to forest fire burnt patches also. So this actually gives us the burnt area discrimination. So for this particular task, we have to actually see the pre-fire condition. The pre-fire condition, suppose we are taking November, where vegetation is at its peak growth in this region, and then we also compare the image with the post fire, like during the fire season. Here fire season lasts from say January end to up to May. So and March or April is the peak time where forest fire occurs maximum. So that's how we have taken a VH polarization to see the change in the volume component of the forest. And then this is a polarization, it is observed. But you see here in the VH component, the same area, these patches are clearly visible. So these are actually the blank patches, which are a result of the forest, burning of the patches for the cultivation. So in the VV, and then we have generated what is called a ratio of the post fire to the pre-fire, and to observe, to get the maximum information. So here the cross-polarized data is used. Here a VV component is used, but it is observed that the VH component is giving us better discrimination and we get the better delineation of these burnt patches. So now, as I have mentioned here, the ratio of these images, there are several ratios nowadays actually are available. When we use optical data, actually through the experience and several studies have been carried out, there are several indices available with the optical bands, say with red band and infrared band. One of the famous index that is used is the normalized difference vegetation index, the NDVI, which uses NIR and the red component of the optical bands. Because what is happening here, NIR gives a very good discrimination, whereas red is absorbed. So a difference between these two will give the forest the characteristics of the forest. But in the radar images also similar indices are being generated, which are used for the for various studies. Two such examples are the radar vegetation index and the radar forest degradation index. So here what is happening here is that we use HV component and a ratio of the polarizations is generated, and how this ratio is helping us. This RVI is 0 for bare surfaces, as we see, and as the forest increases, it approaches 1. And that's how in a particular image we can see what is the level of, even it can be used in the deforestation studies also, and how much forest is available in a particular area. Next, we have the radar forest degradation index (RFDI), where it is a ratio between the HH and HB polarizations. And the important thing what we need to understand here is that here the deforested areas, the value will be high, and whereas in forested area it goes on increasing. It ranges up from 0 to 1. When canopy opens up, RFDI value goes up, and lower RFDI indicate level of forest canopy cover and intactness. So these are two important indices that we can practice. So in the forest study, there are certain recommendations based on the various interaction of the radar parameter and the surface parameter, that shallow angles provide better discrimination of the forest cover mapping and preserve mapping, and steep angles provide better distinction between forest versus non-forest in flat areas. Dry season is actually preferred for discrimination between the forest. Why dry season? Because there will be leaf fall in the forest, and that's how when we use the particular band, it will clearly discriminate between a deciduous forest and the evergreen forest. And also in dry seasons, even C band also can penetrate to a certain extent within the forest for the biomass estimations. And definitely multi-temporal data sets are always used for studies like deforestation studies, and we need to have a choice of polarizations and the incident angle, particularly when we are taking up the forest study. So now we have the certain techniques like interferometric techniques that I will not discuss here, just to give a glimpse and why it is important, because it can further improve the height characteristics of the forest, and that is very important for the regions like northeastern region, where the topography plays an important role, and accordingly the forest height determination all will play an important role. So this is a combination of the interferometric technique and the polarimetric technique. So now, when we see the future, some future the SAR data which are coming which are mainly focusing on using the P band. It is mainly being taken up for the biomass estimations. As I have said, that biomass estimation is very important for any particular forest region that plays an important role in the climate study. So considering the importance, the P-band based satellite is coming up in the future. And again, the L-band data also we are going to get. Then S-band also we are going to get. And reset is Indian satellite. And important is that NISAR, but the Indo-US collaboration, where we are going to get a L-band and the S-band data set. So in future, all this will be very, very useful for the SAR-based studies. So as I said, the timing plays a very important role in the forest-based studies, because one thing is that here when you have the deciduous study where there is a leaf fall, and suppose you are using data when you are saying like there is leaf fall, but you are using that particular data. So it is often it happens that leads to a wrong interpretation. So that's why we should be very, very careful in selecting the timing of the data that we select. So with that, we come to the end of this particular presentation on the forestry, how this SAR data can be used. So maybe if you have something now we can discuss, or later also it is possible to discuss. Hope this presentation was useful to you.